Hello, welcome back to Dinosaurs. We're going to keep walking through the Saurischia with our last group of the theropod dinosaurs, the Maniraptora, and into the Maniraptora, and we're going to see dinosaurs actually taking flight today. Then we're going to go to dinosaurs that most definitely did not fly, the sauropodomorphs and the massive sauropod dinosaurs. That's going to be the end of Saurischia, and then we're going to go into the next module, the Ornithischia, the other dinosaur clade that we haven't talked about yet. Before we do that though, so some announcements. Hopefully none of that is news to you. Let's review where we were before. So the Coelurosauria, we started talking about them last time. Coelurosauria means hollow-tailed lizards because, what do you think? Why are they called hollow-tailed lizards? And the correct answer is their skeletons have air pockets, so their vertebra and some of their other bones start being pneumatized and just full of air pockets to reduce their weight, and eventually that allows them to fly, which none of the other dinosaurs that we've talked about have been able to achieve that. They definitely have tails initially, although in modern birds the tail is fully reduced and only present with the feathered tail, which isn't actually bony. Their tails are not made of cartilage, and they definitely don't drop their tails to escape as like geckos and things like that. So it's because their skeletons have air pockets. Which coelurosaurs likely had feathers? So we talked a lot last time about certain coelurosaurs having pretty decent evidence for feathers, some direct evidence for feathers, and some with evidence for scales. Which ones probably had feathers? Here's an example of T-Rex here, T-Rex being a very large theropod coelurosaur. So which ones probably had feathers? Probably the small, well, definitely the small coelurosaurs. So there's a lot of direct evidence in the smaller body forms, and that's kind of what you'd expect. So remember, the larger forms tend to be able to regulate their body heat just because they're large. The thermal inertia prevents them from either heating up too fast or cooling down too fast just because they're really big. Small coelurosaurs don't have that luxury, and so they need some sort of insulation in the form of generally feathers. In some cases, feathers as we sort of think about them today, but in other cases, sort of like more of a fuzz, almost like a sort of fur, but in feather form. But potentially all coelurosaurs, some of the basal members already have feathers, and so the implication is that those that came afterwards may have feathers too. If the very early coelurosaurs had feathers and the living coelurosaurs, birds, have feathers, all coelurosaurs in between have feathers? Well, remember that evolution can gain and lose these different features. Large coelurosaurs probably either didn't have feathers or had reduced covering of feathers. There's no direct evidence for feathers in, say, Tyrannosaurus rex, the largest coelurosaur, but Tyrannus, which isn't all that much smaller, does have evidence of probably full body covering of feathers, so keep that in mind. All right, so let's look at the theropoda diagram. We've already talked about all of these other theropods, so we've come a long way in the last 2 weeks. And we're going to talk now about this coelurosaurs. We're going to dive further into this group. So remember, Coelurosauria means hollow-tailed lizard. They are by far the most diverse and numerous dinosaur clade, and that's why we're spending 2 days on them. In retrospect, we probably should have spent 3 days on them. But it spans all the way from the massive Tyrannosaurus rex, the biggest of the theropod dinosaurs, probably the largest macrocarnivore of all time. Spinosaurus is probably a little bit bigger, a little bit heavier, but it was mostly feeding on fish, so it's piscivorous, not carnivorous. All the way down to the tiny little quote-unquote raptors, particularly Microraptor, one of the smallest dinosaurs, one of the smallest non-avian dinosaurs of all of them. So this group is very diverse. A lot of different body plans, a lot of different body forms, and a lot of range of size and shape and function and lifestyle. So Coelurosauria is a very large very diverse group. Unlike almost all of the other previous clades, Coelurosaurs are not all carnivorous. There are many omnivores in this group, and there may even be some full herbivores. And the group does include Aves, the modern birds. So technically, Coelurosauria are not actually extinct. They're the only clade of dinosaurs that still exists today in the form of Aves, the modern birds, although some people like to draw kind of a line between the Coelurosaur dinosaurs and birds. They are the same lineage, and so they are still technically alive. So let's zoom into the Coelurosauria themselves. We talked about Carnosauria, which are not Coelurosaurs before. The first branch here, we talked about the Tyrannosauroidea. We talked about the Ornithomimosauria, the bird mimics. Now we're going to start into the rest of the group here. We're going to start over here with the Therizzinosauria, then the Alvarezosauria, and then we're going to talk about the Maniraptora and the Oviraptorsauria as we get kind of closer and closer to Aves. This is the trend towards modern birds. So let's start with the Maniraptora. So Maniraptora translates to hand snatcher. Previously we said raptor means like thief, and that can mean that in the context or to snatch or to grab or to seize, to steal. So Maniraptora hand snatchers, something like that. In this group, we begin to see a lot of the more derived characteristics that we'll see in modern day birds. This group really starts becoming very bird-like. So like tyrannosauroids, they look a lot like Tyrannosaurus rex. Many versions of Tyrannosaurus rex, that's very much a theropod dinosaur body plan, a big carnivorous theropod dinosaur body plan. You can see a lot of the similarities with that in birds, but now we're really going to start seeing similarities with birds. Unlike the tyrannosaurids, we're going to see a trend towards longer arms instead of the reduced arms. We're also going to see a trend towards more elongate, grasping hands instead of the reduced hands like we saw with tyrannosauroids. We're also going to see semi-lunate wrists, where the wrist, instead of flexing in kind of this plane, is going to start flexing like this, kind of the front back. It actually kind of hurts to do that because we don't have semi-lunate wrists. We also start seeing the sternum, the chest bone here, get a lot larger and a lot bonier to support the big muscles of the arms to start doing the kind of flapping motions. Initially, it's probably more for like the grasping motions, but eventually that develops into the flapping motions that birds need to support powered flight. One thing we also see is that we start seeing the backward facing pubic bone, so that hip bone. Remember that the big two major groups of the dinosaurs, the ornithischian bird hip dinosaurs, have that backward facing pubis. The Saurischians have generally a forward facing pubis. However, these are Saurischian dinosaurs that we're talking about here. They independently, convergently start aligning towards this backwards facing pubis. And so remember that even though they're called the Ornithischia bird-hipped dinosaurs, birds themselves, Aves, are actually Saurischian dinosaurs, not Ornithischian. So that's obviously very confusing. So try to keep that in mind. Birds independently later converge on that same type of hip there. And also we start to see some move away from like the musculature of the legs being tied into with the tail and the femur, which is really more kind of like power stroke to give the dinosaur like power and strength. We start seeing the musculature being kind of more associated with the femur and the knee, which is built more kind of towards speed. You see here are some examples of this body form. We're seeing this kind of longer, slender body with longer grasping hands, longer, slender legs built for running, built for speed, as opposed to the power that we've been seeing all along. We also start seeing reductions in teeth, kind of moving more towards beaks, but not necessarily always. So there's a lot of reversals of this trend. But again, here's this semi-lunate carpal, the kind of this kind of motion, very much more extreme. I can't do it obviously, or I'd break my wrist. And I'm not going to do that for you, sorry. So let's look at this first group here, the Therizzinosauria. So we're going to talk about Falcarius, and then we're going to talk about the Therizzianosaur itself. So Falcarius translates to sickle cutter, and it's an early Cretaceous, very basal Therizzianosaurian from the Cedar Mountain Formation, which is in North America out west. So if you look at Falcarius, you can see kind of where its name comes from. There's a house cat there for scale, so this is not a massive dinosaur. Unlike a lot of the theropods that we've seen up to this point, this probably has a mostly herbivorous diet, even though we see, looking at the skeleton here and looking at the reconstruction, we have these fingers with these pretty scary looking claws. Those clawed hands probably are not used primarily for predation, carnivory. They're probably mostly used for stripping leaves off of trees. So similar to like a modern day sloth, sloths have very scary looking claws, but they don't use them for tearing apart flesh. They use it for tearing apart leaves, or like modern day anteaters, they use them for tearing into termite mounds to eat insects. And so this is probably what these lifestyles are here. One interesting thing about Falcarius is that the specimens are often found in bone beds, single beds, which represent like one big depositional event with just hundreds of individuals in there. And again, kind of ranging in size, as we talked about with the trace fossils. A good indication of herding behavior is not only that you see a lot of individuals, but that you see a lot of individuals of varying sizes, which means that they're varying stages of growth. And so these are family units that are traveling together. And so Falcarius probably had sort of a herd, or since we're starting to get more towards birds, you might want to call it a flock. So they probably were in kind of social groups. But again, you kind of see these massive claws here, which are typical of this group. Then we get into Therizzianosaurus. It translates to reaper lizard, and I think you can kind of see why. It has these very long, very pointy, very elaborate claws, and you see the size here. This is a very large dinosaur. It was initially only known from the claws, and initially it was interpreted as this kind of weird gigantic turtle with these big old claws for digging. So it was recognized pretty quickly that, you know, a claw this long and this slender probably isn't a like slashing type of claw. If you think about like a cat claw or something like that, it's hooked, but it's pretty robust. Or if you think about like the claws on Velociraptor, which we'll see a little bit later in the lecture today, those are claws that are designed for ripping flesh. These claws, if you were using them for that purpose, they would probably break. So they're used for stripping vegetation, again, like a sloth, or digging into mounds like an anteater. This reconstruction here you see doesn't have the feather covering on there. It says it's been deliberately omitted. Why would it be deliberately omitted? We know that other very close relatives here have feathers. Well, this is a large-bodied coelurosaur, a large-bodied theropod coelurosaur. Do the large-bodied all have feathers? Do they have some feathers? Are they fully feathered, as in this reconstruction here? I think it says here, gloriously derpy, not deadly, something pigeon. This is probably not accurate, the full body on the large body, but full-bodied feathers on the large-bodied theropod, but maybe. Again, feathers are very unlikely to be preserved in the fossil record, and we have scant little peeks at it. And was it, who knows? So we have educated guesses. We have preserved on some species, but how far away from those species are we willing to extend that information is a matter of interpretation, and all that can help us is new fossils, new discoveries, and better understanding of how these organisms are related to each other. That's why we keep looking at these cladograms. That's why we keep investigating how these things are related to each other, because if we know the ancestry and how these things are linked, we can start making predictions and educated guesses, and we can start testing those predictions as we get new fossil material. It's one of the ways that we know that evolution works. It's one of the ways that we know that cladistics works. We see these relationships, and we have organisms with like less complete information. We make predictions about what they might look like. As we discover more material, our predictions are either confirmed or denied using information from predictions about their evolutionary history. Back to that cladogram. So now we're going to talk about Alvarezsauria. We got a lot of dinosaurs to talk about today, so we're going to move a little bit quickly here. Haplokyrus is the first Alvarezsaurian that we're going to talk about. It translates to simple-handed. It's from the late Jurassic Shishugou Formation in China, and it's significant because it's a very basal Maniraptoran, so it's one of the earliest forms of this major group, and it has the 3-digit hand. So again, the pinky and the finger here is reduced, then you got the 3-digit hand with a really long thumb claw and very kind of nimble fingers for catching prey or possibly kind of digging into trees and stuff, like you see very much with, like, again, anteaters. This particular reconstruction here is kind of downy feathers. Here you see it again. They are probably covered in downy feathers. There's evidence for feathers in this particular specimen, particular organism. But again, you see relatively small. So if we think about the general trend of size that we saw in the Tyrannosauroids, over time we had this trend towards kind of larger body sizes, reduced forelimbs, reduced fingers. In these Maniraptorans, we're sort of seeing the opposite trend, where we're seeing sort of a trend of generally reduced body size. We're going to see some examples where that's not always true, but in general, these dinosaurs are getting smaller and lighter and faster and more bird-like. We're heading that direction on this evolutionary tree. And now Alvarezsaurus itself, it's named after an Argentinian historian, so it's not Luis Alvarez, the one who made famous the Chicxulub impact crater, known from the late Cretaceous of Argentina. And if you look at the reconstructions here, the thing that jumps out about Alvarezsaurus is it has this very weird hand. It has one very large claw, the third and the first digits are reduced, and it has this very large claw on the second finger, and it has really short, stout arms. What this was used for, looking at these reconstructions, what could it possibly be useful for? It's difficult to say, but the arms are short and well muscled with a pretty good strong point at the end, probably for digging, something like that. But in some cases, the functional morphology can sort of break down if we don't have like modern analogs. I can't really think of a modern animal that has like this one bony arm like that. It's kind of goofy. So going back to the Coelurosaurian cladogram, now we're going to talk about the Oviraptorosauria. And so we're going to talk about Caenignathus, which translates to recent jaw, and it's named for its kind of toothless bird-like beak. It has a beak, a jaw that very much resembles modern birds, and initially it was interpreted as a modern bird. That's where the name comes from. So it's from the late Cretaceous of Alberta in the Dinosaur Park Formation, and we talked again about that lunate, semi-lunate wrist that allows the wrist to move in this plane as opposed to this plane. They start having this very well-developed lunate wrist, and we're going to see that continue on in the next dinosaurs that we look at. And again, the musculature of the legs, we don't have this big old dino butt here linking the tail and the legs. The musculature is really more to do with the knee. Again, more of adaptations for speed and running, something like we see in modern flightless birds like ostrich and emu, and maybe like cassowary, things like that. So up until this point, we could really kind of take the dinosaurs and we could really kind of compare with human anatomy fairly easily. Like, you know, I've been doing the motions with the fingers and things like that. Although sometimes when we get to like middle finger and they only have 3, but there's some complications with it. But so far it's been pretty easy to like link up like dinosaur anatomy with other tetrapod anatomy with relative ease. But now these things are really becoming highly specialized and sort of pretty different from other tetrapods. So think about like a crocodile versus a human. You can kind of imagine a human down on all fours, and you can imagine the morphological similarities. But when you start looking like a bird versus a human, it's hard to link things up because they're very different. They're very highly specialized. And so this is a picture of a flamingo in life position. And these are the bones of a flamingo, a modern bird. This is a human here, a nice little drawing here, a very amusing drawing, at least I find it pretty funny. This is a human trying to mimic that form. And so you see like awkwardly bending the wrists backwards, trying to stand up on tippy toes here, but they can't look like a flamingo because they don't have the same proportions as a flamingo. So you have to kind of stretch the human out into these kind of grotesque proportions to mimic this. So remember the kind of backwards bending quote unquote knee of these walking birds is actually the ankle. And then these are the foot bones here, and these are the toes that are balanced out here. The knee is way up here, which as you can see on the flamingo, the knee is there. So you have to kind of stretch the human out into these proportions to meet those this weird morphology, this new specific morphology that we're going to see continue with the birds. Same thing with the wrist here. The shoulder kind of comes back more. The forearms are more elongated. And then you see the wrist kind of really, this person's wrist here is broken. It's facing backwards too far. Humans can't do that. But we start seeing this trend in these, this movement towards the the dinosaur transition here. Next dinosaur we're going to talk about, Oviraptor. We've talked about this Oviraptor before. So Oviraptor Phyloceratops means egg thief, lover of ceratopsises. And remember that this fossil that was found in Mongolia was originally interpreted as an act of predation, where this horrible, nasty, clawed, carnivorous, vicious dinosaur is predating on these poor defenseless eggs. And later it was found that inside the eggs are little baby oviraptors. And so rather than being this thief that was trying to eat these eggs and destroy these eggs, it was protecting these eggs. And you see again the eggs kind of laid out in this kind of radial pattern with the dinosaur sitting on the nest with the arms outward, kind of cradling it. Again, you see this kind of backwards flexing wrist, very typical of these now moving towards the bird transition. We still have the claws, significant feathers, feathers on the forelimbs. Are these flight feathers? No. So if they're not flight feathers, why do they have feathers at all? Well, they're sitting on this nest and they need to keep heat in. The feathers on the arms are a great way to do that. So flight is not the only reason that feathers exist, and insulation is not the only reason either, or at least insulation of the body. We also need to think about the adaptations for brooding. And then also, even if you can't fly with your wings, in some cases you can glide or at least slow down your fall, or you can use it to kind of run up inclined surfaces that you otherwise wouldn't be able to do, just to get away from predators. So wings, arms don't need to be able to fly to have feathers be an evolutionary advantage. And this is a really good example here. Oviraptor was definitely flightless, it couldn't fly, but the winged, the feathered arms were very useful for brooding. And that brings us to Caudipteryx. which is translates to tail feather. And from the fossil here, you can obviously see why. We're starting, again, we see a trend towards more derived, more advanced bird-like characteristics. One of the characteristics of modern birds is that they don't have elongate bony tails. The tails are reduced and they're ended with that pidgeot style, and the tail feathers kind of flare off from that. We see a trend here towards this. The tail is shorter than a lot of the other Coelurosaurs that we've seen, or even theropods that we've seen. It's shorter, but it's definitely not short, but it is tipped with feathers, and so we're trending in that general direction. We also don't see really like a true beak, but it has a beak-like jaw, and it does retain a few teeth. And so unlike modern birds, which have just a beak without teeth, probably to save on weight for flying, this still retains some teeth. Again, some very ancestral, basal, more reptile-like features. And we're transitioning and we're adding kind of more and more derived, advanced bird features. We also see in this case that the feathers themselves are evolving. Instead of the very primitive kind of downy plumaceous feathers, we're starting to see pennaceous feathers with the actual barb and the veins, actual veined feathers. We're starting to see the asymmetry of the feathers that we would actually be using in flight, but still this thing is probably not capable of flight, almost certainly not capable of flight. You see it probably has just the tail feathers and sort of very limited arm feathers and probably the downy plumaceous feathers over the rest of the body, but we're getting more and more bird-like. And so now we're going to jump into this last category of the Coelurosaurias, the U Maniraptora. So U Maniraptora translates to true hand snatchers, or true hand grabbers, or true hand seizers, to seize. And so the Maniraptora showed a lot of the bird-like characteristics. Now we're going to start seeing many of them, and eventually we're going to see all of them because birds are Eumaniraptorans. We see a lot of these more derived traits of birds. Again, highly elongated arms. We start to see arms that in many cases are longer than the legs. Then the forelimbs are starting to become longer than the hind limbs, because if you're going to develop flight, you need that. You need a wide, long flight surface. We also see elongated hands, elongated fingers. Eventually, these are the mounting surfaces for the flight feathers. And so again, this is a thing that we see in birds. This is, yeah, okay. We also start seeing a backward-facing, quote-unquote, big toe. So again, it's getting kind of hard to compare human anatomy to these, but the digit 1 on the foot starts to kind of point backwards, and it's also a little bit reduced. It generally doesn't touch the ground here. Eventually, that becomes kind of the grasping toe. Like if you think about a modern bird foot, that grasping, this is that backward-facing big toe. And we also again see that backward-facing pubis bone. The Saurischian lizard-hipped dinosaurs have evolved towards the quote-unquote bird hip. Another feature that we see in a lot of these is this retractable second digit. So we have the thumb sort of reverting backwards, and we have this retractable able to pull up. I can't do it, obviously. It'll break my finger. And then we've got these 3 digits here, but the pinky's lost in all dinosaurs, so really it's only these 2 digits. And that's often topped with a large claw, so kind of the quote-unquote index finger on the foot, I don't know what index toe, is often tipped with this large killing claw, as we saw on the Velociraptors tap, tap, tapping on the ground menacingly in Jurassic Park. We're going to be talking about Velociraptor pretty soon here. Troodon, or I guess I should say Troodon, Troodon, translates to wounding tooth, from the late Cretaceous of Alberta. Again, the Dinosaur Park Formation, Dinosaur Park Formation. Lots of different dinosaurs that we've mentioned today are coming out of this Dinosaur Park Formation, and I think we're going to talk about it a little bit later in the class when we get to start trying to look at ecosystems as a whole. We're just trying to see these individual dinosaurs, individual trends, but we're going to start talking about ecosystems as a whole. How are they relating with each other, and what's that environment like, and how are they relating with the environment, et cetera, et cetera. So wounding tooth is named for these sort of very unusual serrations of the teeth. Initially, it was kind of thought of like this is like a hyper carnivore kind of thing, but really we see these serrations on a lot of herbivorous or omnivorous dinosaurs as well, for like cutting leaves and the hard carapaces of insects. And so in this case, it's probably actually an omnivorous trait. And so again, we're seeing this trend towards omnivory away from macrocarnivory. These things are becoming kind of less and less carnivorous and more omnivorous. And again, the body size tends to be getting kind of smaller and smaller and smaller as we move towards birds. And as we find out later, the birds survive the big mass extinction at the end. This trend in being more generalist in their diet, more omnivorous, smaller body size with insulation of feathers. These are probably the traits that allow these dinosaurs to survive. Another thing that we start seeing here, we've seen this trend kind of all along. Tyrannosaurids have relatively large brains for their size. T-Rex probably has the largest brain of all the dinosaurs based just on its really massive size. But Troodon has a large brain relative compared to its very small size. And that's often been linked with like rough estimates of intelligence, although in some cases that doesn't necessarily hold up, and it might be like complexity of the brain that's a little bit more important. But their ratio of brain size to body size is on the order of modern birds. And although people use bird brained as sort of an insult, birds are highly intelligent. Corvids, like crows, are very capable of solving problems and even using tools. There's some examples of them using like palm fronds to kind of hook things out of crevices. They're very highly intelligent, very good problem solvers. Birds are quite intelligent, and that's what we're starting to see here in these dinosaurs that are getting closer and closer to birds, is that they're getting lighter, they're getting smaller, they're getting more agile, they're adding feathers, the feathers are becoming more advanced, and they're also getting smarter. To fly in 3 dimensions in the air takes a lot of calculations in the brain, and it requires a lot of computing power, and we're starting to see that trend here. Now, a dinosaur that probably a lot of you have been waiting for, Velociraptor. So Veloci is swift, it's like velocity. Swift Caesar, swift grabber, swift thief, if you want to use that other translation. They're from the late Cretaceous of, I should say Mongolia, not there, Mongola. It was originally referred to as Ovoraptor, which would have been very unfortunate given Oviraptor, which we just talked about a little while ago. Fortunately, they thought better of it and changed it to Velociraptor. Otherwise, Oviraptor is also from Mongolia. We've been trying to differentiate Oviraptor from Ovoraptor. I'm glad that I don't have to do that. Obviously, Velociraptor is the most famous quote-unquote raptor. And this group of dinosaurs, these dromaeosaurs, are sometimes called informally raptors. And modern birds of prey are also sometimes called raptors. They're evolutionarily related to each other. They're on the same path, and they're part of this general trend towards more derived bird-like features. And so Velociraptor obviously is very famous from the original Jurassic Park and all the other movies in the series. And they took some artistic liberties by kind of scaling it up to quite a bit larger than it actually is. In reality, Velociraptor is kind of like turkey size, or maybe even a little bit smaller than that. But they're certainly not something to be taken lightly. They have these very prominent sickle-shaped killing claws on toe number 2. And again, dinosaurs are all missing toe 5 toe 1 is sort of back and reduced. The killing claw is on the index finger here, and it is retractable, and we often see them not walking on it to sort of keep that claw nice and sharp. And so we were seeing kind of normally like three-toed dinosaur footprints. Now we're starting to see them kind of keep that other toe sort of off the ground. With that killing claw, they may have used it for like disemboweling and things like that, but it was probably more of like a seize and hold technique where they would like pounce on their prey, pin it down with their body weight and with their really large claws, and hold it down and just hold and just start feasting on it. Modern raptors will often start eating their prey while it's still alive in the clutches of their claws. Sometimes the initial impact is enough to kill it, but not always. So I try very hard not to put a lot of blood and gore in the slides, so just because I know some people are sensitive to that. But this is a very graphic way of eating, and we see this continue in modern day birds. But you see, these are the Velociraptors of Jurassic Park fame. They're, you know, clever girl, and they're working together, coordinating in packs. Just like Troodon, these raptor dinosaurs, they do have relatively large brains for their body size. They're pretty intelligent as dinosaurs go. The big question is how intelligent. Again, we have trouble measuring even human intelligence or the intelligence of modern animals that we can actually directly observe and directly test. So it's difficult to say what they would be capable of. But if any dinosaurs are capable of coordinating and hunting together in packs, it probably is this kind of group of dinosaurs, these raptors. They are carnivorous, and they have the brain power, highest brain power, to be able to maybe be capable of that. Still probably not, but possibly. And what we see is they're probably not these dynamic apex predators, more opportunistic predators. They're not going to take on a T-Rex like in Jurassic Park. They're just not. They're not of that scale. T-Rex could take on 100 of these things. Maybe, I don't know. I guess maybe eventually it would die from 1,000 cuts, blood loss. But also, they're not going to fight. Remember, carnivores are not going to try to deliberately fight each other just to prove their worth. And also, these are on Mongolia. They're in the Asian continent, and T-Rex is the North American continent, and they're also separated by several million years in time. Moving along onto the raptors, Deinonychus translates to terrible claw, and obviously, just like the Velociraptors, you can see why, that killing foot claw on the second digit. These are known from the early Cretaceous of the Western US, and they really kind of brought this bird dinosaur link back to the general scientific community. So John Ostrum, very famous paleontologist that worked in the Western United States in his late 60s, he started noticing a lot of similarities here between Deinonychus and these raptor dinosaurs and ostriches, modern ray-tight birds, the flightless birds, and birds of prey, raptor birds of prey. And it really started this dinosaur renaissance where, remember we've seen this transition from these big plodding, cold-blooded, four-legged lizard forms initially, and we see over time more of this evolution towards bipedal, more energetic, more active. This is sort of the transition to very like warm-blooded, bird-like, highly active, very fast, very agile, dynamic hunters. And this is really this kind of sea change here, this dinosaur renaissance. It wasn't the first person to come up with it though. So Huxley, who was a contemporary of Darwin, so going all the way back to the very beginnings of origin of species and evolution, there were these comparative anatomy leaps of like, wow, dinosaur fossils really kind of resemble birds in a lot of different ways. It didn't kind of catch on. Our good friend Marsh from the Bone Wars put it forward again too in 1877, this hypothesized link between dinosaurs and birds. So it wasn't unheard of, but it was really about 100 years later that it really started gaining some traction. And really only in the last like 2 to 3 decades has it really, really caught on. And you started seeing dinosaurs with feathers in pop culture and media, and reconstruction starting to feature feathered dinosaurs. Maybe too many feathers in some cases. So there was this trend to make T-Rex fully covered in feathers. Again, all of the integument, all of the body covering of T-Rex that we have is scales, but we don't have all of the body preserved. And so maybe there are some feathers, particularly probably along the head and back of the neck and back. That's where you'd maybe expect it. So, but this Deinonychus was very important for bringing that back to the scientific forefront. And again, you see the reconstruction here, highly feathered with more pennate feathers on the arms and more maybe plumose feathers on the body with, again, pennate feathers on the tail. And this is just a skeletal comparison between Deinonychus and an ostrich. The feet here, they've taken a couple liberties here with the feet of the ostrich. Ostrich have, pretty pronounced claws on their feet, but not to this degree. I think they're just putting the bird anatomy onto that. But you can see a lot of similarities here. Again, the slender hind limbs, the elongate lower limbs, elongate ankle, the different claws with the backward facing big toe to form like the grasping of perching birds or the running of these running birds, that second digit there. And we also then see that kind of folded back, again, the semi-lunate, in this case, highly lunate wrist that allows the hand to kind of fold backwards on itself down kind of along the lower arm. Another very famous example of these quote unquote raptors is Oviraptor. So it translates to Utah Caesar. It's from the early Cretaceous of, I wonder where you could find Oviraptor. It's from Utah, the Cedar Mountain Formation. It is the largest dromaeosaur raptor. So when we think about Jurassic Park's raptors and kind of the error in making them kind of too big and maybe too like fierce, Oviraptor was on that scale. And it was also kind of discovered right around the time when Jurassic Park was being made in the early 90s. And so it might have been sort of an influence. They had found claws that were twice as large as the claws that they were known from Velociraptor. And so that was sort of known at the time. And so they probably took some artistic liberties in scaling up Velociraptor. But Oviraptor probably was along that size. And so it's this very large, very dominant predator. It's now Utah's official state dinosaur. So they voted it replaced poor Allosaurus. So we talked about Allosaurus back with the Carnosauria. Allosaurus has been displaced by Oviraptor. Seems fitting for Utah though. At the time of discovery, they were actually considering naming it Oviraptor Spielbergi, to try to maybe pull in some funding from the deep pockets of Steven Spielberg at the height of kind of Jurassic Park's fame, but then they thought better of it. So they never ended up doing that. But this is a very large raptor, but you can see that. So like they portray raptors kind of taking on T-Rex in there. And do they actually take it down? I think they do. The size comparison here, obviously it's more favorable than Velociraptor would be, but there's still a pretty big mismatch here. It would take several of these working together and coordinating to take down a T-Rex, which again, maybe they're capable of that, maybe they're not, but why? Why would they do that? Why would they work together to fight one of the most formidable carnivores of all time? They're not trying to prove anything. Dinosaurs never just flex for it. Carnivores are very wary of taking on other carnivores. There's no benefit for it. Even just hunting their prey is very dangerous. We're going to talk about sauropods. We're going to talk about the ornithischian dinosaurs. Even just finding food is dangerous. These things have a lot of defenses. You don't want to take unnecessary risks. A broken jaw, a broken leg, a broken claw, that's a death sentence in some cases. So just keep that in mind when you think about these dinosaur fights. They generally don't happen. We do see fights between large carnivores in nature now, again, generally over territory, over mates, or potentially over food. They're not just going to fight for the hell of it. It's very dangerous. And then Dromaeosaurus, swift-running lizard from the late Cretaceous of Alberta and, again, Western United States. Its namesake for this group of dromaeosaurs, they're collectively known as the raptors. Even though it's the namesake for the group, it's a relatively poor fossil record. It is a sister taxon to Dakotaraptor, which is slightly larger, but again, nowhere near the size and scale of taking on a Tyrannosaurus rex. But again, one of the cool features of these raptor dinosaurs, you see the backwards facing big toe, the enlarged retractable second toe that they can actually pull kind of backwards off the ground to try to protect that claw from being worn down by dragging on the ground. And so up until this point, theropod footprints were generally three-toed. You start to see Velociraptor pulls that toe up, Utahraptor pulls that toe up, Dromaeosaur pulls that toe up, Troodon pulls that toe up. They're trying to protect that big claw. That's their living there, is that killing claw that they use to feed and they use to hunt. They don't want it worn down, dragging on the ground, so they actually protect it by pulling it backwards and up off the ground. And so you start leaving only two-footed or two-toed footprints. And the last of these raptors that we're going to talk about is Microraptor, the small Caesar from the early Cretaceous Liaoning Formation in China. It's a four-winged dinosaur. It has feathers on its arms and it has feathers on its legs. And it's also one of the smallest known non-avian dinosaurs. You see the fossil here still has the really long tail, so we're not quite to all of the bird features yet. There's a lot of debate about whether this thing was capable of powered flight. It was probably capable of at least limited gliding, but there's a lot of debate about whether it was capable of actually flying and lifting off the ground. It's among the smallest non-avian dinosaurs. You can see the size here, smaller than even like a chicken. You can see the other raptors here. Here's a Velociraptor, again, pretty small. Utahraptor though, or sorry, this is Ostroraptor. This is Utahraptor. Now we're getting into the bigger raptors. Number 4 here, Dromaeosaurus, and number 6, Deinonychus, who we also talked about there. Now back to the cladogram here. We're going to talk about Archaeopteryx and Anchiornis. This Maniraptor, again, true hand snatchers. We already talked about this. We show the foot here. So Anchiornis translates to near bird, and it's known from hundreds of specimens. So there's lots of different specimens of Anchiornis from the Taojinshan Formation in China. A lot of similarities to dromaeosaurids, a lot of similarities to troodontids, but also a lot of similarities to primitive birds. This is kind of inching towards that transition towards birds from the raptors. The raptors have a lot of bird-like traits, but they weren't flying around. They weren't gliding. This is probably getting nearer to that lifestyle. And again, just like we saw with Microraptor, both the arms and the legs are feathered. And there's even been pigments extracted from these feathers to kind of get an idea of the colors. It was probably mostly gray-black with some white striping. Probably just a glider, though. There are, again, some reconstructions, again, some debate about whether this thing was able to fly, but the general consensus is that it was able to glide. And so you climb up the tree and you glide like a flying squirrel or a Draco lizard or something like that. Or it's useful for if you're trying to get away from a predator and need to get up a tree. If you flap your wings and kind of press your feet up against a tree, they can actually do this kind of wing-assisted incline running, where they can actually run up the steep side. So you'll sometimes see chickens do this in the barnyard. If something's chasing them, they'll kind of run at a surface and kind of climb up it, flapping their wings to kind of press themselves against the surface and get traction. It's just another way of getting away from predators. It's an evolutionary advantage. They're not actually flying, but it's a new way of escaping, a new way of not living, and living to see a new way of not dying, I should say, and to live to fight another day, live to pass on your genes to next generation. these early wings that may not have been capable of powered flight still have their evolutionary advantages, and over time they're favored. And eventually we get to Archaeopteryx, ancient wing or ancient feather, from the Solnhofen limestone, this exquisite preservation in this lithographic limestone that's used for lithographic prints. It was originally known from just a single feather, so Archaeopteryx was originally named from just a feather sample. And you can see here from this reconstruction, Archaeopteryx is usually regarded as the first kind of true bird, but it still has a lot of features of dinosaurs. It still has a bit of a tail, it still has teeth, it still has the clawed fingers, but we're really starting to see, like, okay, this looks like a kind of weird bird, and it's often, this is the start of birds, Archaeopteryx. And so from here, we move into Euornithes, the true birds. This is modern birds and all their closest relatives during the Mesozoic. This branch of birds goes extinct at the end of the Mesozoic. These linger on, or at least their ancestors linger on into the present. You can see all of these different bird forms that were around during the Jurassic, during the Cretaceous. Birds didn't wait until the dinosaurs were gone to diversify. Birds didn't wait until the pterosaurs were gone to diversify. They diversified after Archaeopteryx. They diversified during the Mesozoic. There's a lot of birds alive alongside dinosaurs. They're probably filling those smaller roles of the flying smaller predators as pterosaurs are becoming larger and larger and larger and larger. And what we see is that those large, ornate, head-crested pterosaurs don't make it through, and the smaller, more generalist, feathered birds do, and that's probably why. And so that's all we've got. Today we'll talk more about birds a little bit in the future here. I hope you enjoyed that lecture, and goodbye.